Optimizing Python Dictionary Access Code. Question. I've profiled my Python program to death, and there is one function that is slowing everything down. It uses Python dictionaries heavily, so I may not have used them in the best way. If I can't get it running faster, I will have to rewrite it in C++, so is there anyone who can help me optimize it in Python? I hope I've given the right sort of explanation, and that you can make some sense of my code. Thanks in advance for any help. My code. This is the offending function, profiled using line_profiler and kernprof. I'm running Python 2.7. I'm particularly puzzled by things like lines 363, 389 and 405, where an if statement with a comparison of two variables seems to take an inordinate amount of time. I've considered using NumPy, as it does sparse matrices, but I don't think it's appropriate because, 1. I'm not indexing my matrix using integers, I'm using object instances, and 2. I'm not storing simple data types in the matrix, I'm storing tuples of a float and an object instance. But I'm willing to be persuaded about NumPy. If anyone knows about NumPy's sparse matrix performance versus Python's hash tables, I'd be interested. Sorry I haven't given a simple example that you can run, but this function is tied up in a much larger project and I couldn't work out how to set up a simple example to test it, without giving you half of my code base. Explanation of my code. This function maintains a sparse distance matrix representing the network distance, sum of edge weights on the shortest path, between nodes in a very big network. To work with the complete table and use the Floyd-Warshall algorithm would be very slow. I tried this first, and it was orders of magnitude slower than the current version. So my code uses a sparse matrix to represent a thresholded version of the full distance matrix. Any paths with a distance greater than 200 units are ignored. The network topology changes over time, so this distance matrix needs updating over time. To do this, I am using a rough implementation of a distance vector routing protocol. Each node in the network knows the distance to each other node and the next node on the path. When a topology change happens, the nodes associated with this change update their distance tables accordingly, and tell their immediate neighbors. The information spreads through the network by nodes sending their distance tables to their neighbors, who update their distance tables and spread them to their neighbors. There is an object representing the distance matrix, self.node_distances. This is a dictionary mapping nodes to routing tables. A node is an object that I've defined. A routing table is a dictionary mapping nodes to tuples of distance, next_node. Distance is the graph distance from node_A to node_B, and next underscore node is the neighbor of node underscore A that you must go to first, on the path between node underscore A and node underscore B. A next underscore node of none indicates that node underscore A and node underscore B are graph neighbors. For example, a sample of a distance matrix could be because of topology changes, two nodes that were far apart, or not connected at all, can become close. When this happens, entries are added to this matrix. Because of the thresholding, two nodes can become too far apart to care about. When this happens, entries are deleted from this matrix. The self.neighbors matrix is similar to self.node underscore distances, but contains information about the direct links, edges, in the network. Self.neighbors is continually being modified externally to this function by the chemical reaction. This is where the network topology changes come from. The actual function that I'm having problems with, propagate underscore distances underscore node, performs one step of the distance vector routing protocol. Given a node, node underscore A, the function makes sure that node underscore A's neighbors are correctly in the distance matrix. Topology changes. The function then sends node underscore A's routing table to all of node underscore A's immediate neighbors in the network. It integrates node underscore A's routing table with each neighbor's own routing table. In the rest of my program, the propagate underscore distances underscore node function is called repeatedly until the distance matrix converges. A set self.nodes underscore changed is maintained of the nodes that have changed their routing table since they were last updated. On every iteration of my algorithm, a random subset of these nodes are chosen and propagate underscore distances underscore node is called on them. This means the nodes spread their routing tables asynchronously and stochastically. This algorithm converges on the true distance matrix when the set self.nodes underscore changed becomes empty. The affinity distances parts, add underscore affinity distance and del underscore affinity distance, are a cache of a small submatrix of the distance matrix that is used by a different part of the program. The reason I'm doing this is that I'm simulating computational analogs of chemicals participating in reactions as part of my PhD. A chemical is a graph of atoms, nodes in the graph. Two chemicals binding together is simulated as their two graphs being joined by new edges. A chemical reaction happens by a complicated process that isn't relevant here, changing the topology of the graph. But what happens in the reaction depends on how far apart the different atoms are that make up the chemicals. So for each atom in the simulation, I want to know which other atoms it is close to. A sparse, thresholded distance matrix is the most efficient way to store this information. Since the topology of the network changes as the reaction happens, I need to update the matrix. A distance vector routing protocol is the fastest way I could come up with of doing this. I don't need a more complicated routing protocol, because things like routing loops don't happen in my particular application, because of how my chemicals are structured. The reason I'm doing it stochastically is so that I can interleave the chemical reaction processes with the distance spreading, and simulate a chemical gradually changing shape over time as the reaction happens, rather than changing shape instantly. The self in this function is an object representing a chemical. The nodes in self.node underscore distances dot keys are the atoms that make up the chemical. The nodes in self.node underscore distances node underscore x dot keys are nodes from the chemical and potentially nodes from any chemicals that the chemical is bound to and reacting with. Update. I tried replacing every instance of node underscore x equals node underscore y with node underscore x is node underscore y, as per Sven Marnak's comment. Sorry, I was doing the profiling wrong. I was using line underscore by underscore line, which, on my code, had far too much variance. That difference of tilde 90 seconds was all in the noise. When profiling it properly, is definitely faster than equals. Using profile, my code with equals took 34.394 s, but with is, it took 33.535 s, which I can confirm is out of the noise. Update. Existing libraries. I'm unsure as to whether there will be an existing library that can do what I want, since my requirements are unusual. I need to compute the shortest path lengths between all pairs of nodes in a weighted, undirected graph. I only care about path lengths that are lower than a threshold value. After computing the path lengths, I make a small change to the network topology, adding or removing an edge, and then I want to recompute the path lengths. My graphs are huge compared to the threshold value. From a given node, most of the graph is further away than the threshold, and so the topology changes don't affect most of the shortest path lengths. This is why I'm using the routing algorithm, because this spreads topology change information through the graph structure, so I can stop spreading it when it's gone further than the threshold. i.e., I don't need to recompute all the paths each time. I can use the previous path information, from before the topology change, to speed up the calculation. This is why I think my algorithm will be faster than any library implementations of shortest path algorithms. I've never seen routing algorithms used outside of actually routing packets through physical networks, but if anyone has, then I'd be interested. Network was suggested by Thomas K. It has lots of algorithms for calculating shortest paths. It has an algorithm for computing the all pairs shortest path lengths with a cutoff, which is what I want, but it only works on unweighted graphs. Mine are weighted. Unfortunately, its algorithms for weighted graphs don't allow the use of a cutoff, which might make them slow for my graphs. And none of its algorithms appear to support the use of pre-calculated paths on a very similar network, i.e. the routing stuff. iGraph is another graph library that I know of, but looking at its documentation, I can't find anything about shortest paths. But I might have missed it. Its documentation doesn't seem very comprehensive. NumPy might be possible, thanks to at 9000s comment. I can store my sparse matrix in a NumPy array if I assign a unique integer to each instance of my nodes. I can then index a NumPy array with integers instead of node instances. I will also need two NumPy arrays, one for the distances and one for the next underscore node references. This might be faster than using Python dictionaries, I don't know yet. Does anyone know of any other libraries that might be useful? Update. Memory usage. I'm running Windows XP, so here is some info about memory usage from Process Explorer. The CPU usage is at 50% because I have a dual-core machine. My program doesn't run out of RAM and start hitting the swap. You can see that from the numbers, and from the I/O graph not having any activity. The spikes on the I/O graph are where the program prints to the screen to say how it's doing. However, my program does keep using up more and more RAM over time, which is probably not a good thing, but it's not using up much RAM overall, which is why I didn't notice the increase until now. And the distance between the spikes on the I/O graph increases over time. This is bad. My program prints to the screen every 100,000 iterations, so that means that each iteration is taking longer to execute as time goes on. I've confirmed this by doing a long run of my program and measuring the time between print statements, the time between each 10,000 iterations of the program. This should be constant, but as you can see from the graph, it increases linearly. So something's up there. The noise on this graph is because my program uses lots of random numbers, so the time for each iteration varies. After my program's been running for a long time, the memory usage looks like this, so it's definitely not running out of RAM.
Node underscore after underscore b equals node underscore a, will try to call, node underscore after underscore b dot underscore eq underscore node underscore a. try to override node._eq_ with an optimized version before resorting to C. Update. I made this little experiment, Python 2.6.6. Results. I was very surprised. .access, ob.property, seems to be very expensive, line 25 versus line 27. There was not much difference between is and equals, at least for simple objects. Then I tried with more complex objects and results are consistent with the first experiment. Are you swapping a lot? If your dataset is so large that it does not fit available RAM, I guess you may experience some kind of I/O contention related to virtual memory fetches. Are you running Linux? If so, could you post a vstat of your machine while running your program? Send us the output of something like. Good luck. Update, from comments by Op. I suggested playing with sys.setCheckInterval and enable/disable the GC. The rationale is that for this particular case, huge number of instances, the default GC reference count check is somewhat expensive and its default interval is away too often. Yes, I had previously played with sys.setCheckInterval. I changed it to 1000, from its default of 100, but it didn't do any measurable difference. Disabling garbage collection has helped, thanks. This has been the biggest speedup so far, saving about 20%, 171 minutes for the whole run, down to 135 minutes. I'm not sure what the error bars are on that, but it must be a statistically significant increase. Adam Nellis, February 9th at 15:10. My guess. I think the Python GC is based on reference count. From time to time it will check the reference count for every instance, since you are traversing these huge in-memory structures. In your particular case the GC default frequency, 1000 cycles, is away too often, a huge waste. Yours truly, February 10th at 2:06.
Have you considered Pyrex, Python? It compiles Python to C and then to PYD automatically, so it might speed things up a fair bit without much work.
I don't see anything wrong with your code regarding performance. Without trying to grok the algorithm, you are just getting hit by the big number of iterations. Parts of your code get executed 40 million times. Notice how 80% of the time is spent in 20% of your code, and those are the 13 lines that get executed 24+ million times. By the way, with this code you provide great illustration to the Pareto principle, or 20% of beer drinkers drink 80% of the beer. First things first, Have you tried Psycho? It's a G compiler that can greatly speed up your code, considering the big number of iterations, say by a factor of 4x 5x, and all you have to do, after downloading and installing, of course, is to insert this snippet in the beginning. This is why I liked Psycho and used it in GCJ2, where time is of essence, nothing to code, nothing to get wrong and sudden boost from 2 lines added. Back to nitpicking, which changes like replacing equals with is etc. is, because of the small % time improvement. Here they are the 13 lines at fault. Besides the lines you mention, I noticed that number 388 has relatively high time when it is trivial. All it does it, node_b_update equals false. Oh but wait, each time it gets executed, false gets looked up in the global scope. To avoid that, assign f_d equals false, true, in the beginning of the method and replace later uses of false and true with locals f and t. This should decrease overall time, although by little, 3%. I noticed that the condition in number 389 occurred only 512,120 times, based on number of executions of number 390, versus the condition in number 391 with 16,251,407. Since there is no dependency, it makes sense to reverse the order of those checks, because of the early cut that should give little boost, 2%. I am not sure if avoiding past statements altogether will help, but if it does not hurt readability. I just noticed you are using try except in a case, number 365 to 367, you just need default value from a dictionary. Try using instead, .get key, default val, or create your dictionaries with, collections.default_dictator_tools.repeat float +inf. Using try except has its price. See number 365 reports 3.5% of the time. That's setting up stack frames and whatnot. Avoid indexed access, be it with obj.field or objx, when possible. For example, I see you use self.node_distances node_a in multiple places, number 336, 339, 346, 366, 386, which means for every use indexing is used twice, once for and once for, and that gets expensive when executed tens of millions of times. Seems to me you can just do at the method beginning, node_a_distances equals self.node_distances node_a, and then use that further.
This would require a fair amount of work, but you might consider using Floyd-Warshall running on a GPU. There has been a lot of work done on making Floyd-Warshall run very efficiently on a GPU. A quick Google search yields this URL, this URL, this URL, this URL. Even though, as implemented in Python, Floyd-Warshall was slower by an order of magnitude, a good GPU version on a powerful GPU might still significantly outperform your new Python code. Here's an anecdote. I had a short, simple, compute-intensive piece of code that did something similar to a Huff accumulation. In Python, optimized as I could get it, it took 7s on a speedy i7. I then wrote a completely non-optimized GPU version. It took 0.002s on an NVIDIA GTX 480. YMMV, but for anything significantly parallel, the GPU is likely to be a long-term winner, And since it's a well-studied algorithm, you should be able to utilize existing highly tuned code. For the Python GPU bridge, I'd recommend PyCUDA or PyOpenCL.
Yes.